Welcome to the Deep Sleep Science channel. Tonight, we are going to explore one of the most fascinating subjects humans have ever tried to understand: physics. Physics is the science that studies how the universe behaves, from the tiniest particles smaller than atoms to the vast structures of galaxies stretching across billions of light years. It asks simple but profound questions. Why do objects fall? What is light? How does electricity travel through wires? Why do stars shine for billions of years? What makes physics especially beautiful is that it often reveals that very different things are connected by the same underlying rules. The light from the sun, the electricity powering your home, the radio signals traveling through the air, and even the glow of distant galaxies are all part of the same family of physical phenomena. Over time, scientists discovered that nature follows patterns that can be measured, described with equations, and used to predict how the world will behave. Many of the technologies we rely on every day come directly from discoveries in physics. Smartphones use quantum physics and semiconductor science. GPS systems depend on precise time measurements and relativity. Medical imaging, lasers, satellites, and even the internet all exist because physicists learned how energy, matter, and waves behave. Physics is not only about distant stars or complex equations that quietly shapes the modern world around us. But physics is also about curiosity. For centuries, people looked at the night sky and wondered how the universe worked. They asked why planets move the way they do, how lightning forms in storms, and what light actually is. Slowly, through careful observation and experimentation, these mysteries began to reveal their answers. Each discovery opened the door to new questions, making physics a never-ending journey of understanding. In this video, we will gently explore hundreds of fascinating facts about physics. We will move from electricity and magnetism to atoms and quantum mechanics, from the structure of matter to the physics of stars, time, and space itself. Each idea will reveal a small piece of the incredible system that governs the universe. Black holes are regions where gravity becomes so strong that once something passes a certain boundary, escaping would require moving faster than light. That boundary is called the event horizon, and it marks a place where the ordinary ideas of leaving or turning back no longer work in the usual way. Black holes are not empty holes in space, but extreme concentrations of mass and warped spacetime. They are among the clearest reminders that gravity can shape the universe in ways that feel almost beyond imagination. Gravitational waves are ripples in spacetime itself, produced when massive objects accelerate in especially violent ways. Instead of traveling through space like sound through air, they are tiny, stretching and squeezing motions of space itself. When enormous objects such as black holes or neutron stars spiral together and merge, they send these ripples outward across the universe. By the time they reach Earth, the effect is incredibly small, but still real and measurable. Einstein predicted gravitational waves in 1916 as a consequence of general relativity, long before any instrument was capable of detecting them. This means the idea existed first as a result of mathematics and theory, and only later as a direct observation. It is one of the great examples of physics patiently waiting for technology to catch up with insight. A prediction written on paper eventually became something humans could hear in the data of real instruments. Merging black holes and neutron stars are among the strongest known sources of gravitational waves because they involve huge masses moving at enormous speeds in tight spirals. As they orbit, they lose energy through gravitational radiation and move closer and closer together. In their final moments, the motion becomes faster and more intense, producing a powerful burst of space-time waves. These are not gentle events, but some of the most extreme collisions known in nature. Gravitational wave astronomy gives scientists a way to study cosmic events using space-time vibrations rather than light. That is important because not everything in the universe shines brightly, and some events are partly hidden from traditional telescopes. With gravitational waves, scientists can listen to the structure of an event instead of only looking at its glow. It is like gaining a new sense for the universe, not replacing sight, but adding another way to perceive it. This opened an entirely new observational window on the universe. For centuries, astronomy depended mainly on light in one form or another, from visible light to radio waves and X-rays. Gravitational wave detection added a completely different messenger, one tied directly to motion in gravity itself. That means the universe can now be explored through more than one channel, and each channel reveals different pieces of the same cosmic story. LIGO detects gravitational waves using laser interferometers with long perpendicular arms. The instrument sends laser light down both arms and compares how the light returns. If a gravitational wave passes through, space stretches in one direction and compresses in the other by a tiny amount, changing the light pattern. It is an elegant design that turns unimaginably small distortions into something measurable. The basic idea is to watch for incredibly tiny changes in arm length as a wave passes. These changes are far smaller than an atom, which sounds almost impossible to detect. Yet physics often works this way. If you cannot observe something directly, you can build a system where the thing leaves a measurable trace. The wave is invisible, but its effect on distance is not beyond the reach of careful instruments. To do that, the instrument must measure length with extraordinary precision using stable laser light. The stability matters because any noise or wandering in the light could hide the tiny signal being searched for. So the experiment becomes not only about gravity, but also about precision, isolation, and control. In many areas of physics, the ability to measure something well is almost as important as the theory being tested. Interferometry works by combining light waves so that tiny phase changes become measurable. When light waves line up, they reinforce each other, and when they are slightly out of step, they can cancel. This sensitivity to small differences makes interferometry one of the most powerful measurement tools in physics. It turns the wave nature of light into a ruler of astonishing delicacy. Sometimes the hardest part of physics is not having a theory, but building an instrument sensitive enough to test it. A good theory can wait for decades or even longer until the right technology exists. This is one reason experimental physics is so remarkable. It turns fragile, hidden, or distant effects into real observations. The progress of science often depends on human patience, engineering skill, and precision just as much as bold ideas. Neutron stars pack stellar-scale mass into city-scale objects, making them among the densest known stars. A neutron star can contain more mass than the Sun, while being only a few tens of kilometers across. That means matter there is compressed to an astonishing degree. These objects show what happens when gravity pushes matter into a state far beyond anything familiar on Earth. The cosmic microwave background originated when the early universe cooled enough for light to decouple from matter. Before that time, the young universe was so hot and dense that light scattered constantly and could not travel freely for long distances. As expansion lowered the temperature, atoms could form more stably, and light began moving more freely across space. The glow from that era still fills the universe today. That happened roughly 380,000 years after the Big Bang. On cosmic timescales, that was very early, yet it was late enough for the universe to change from an opaque plasma into something more transparent. This moment matters because it gave the universe a kind of visible memory. When scientists study the cosmic microwave background, They are studying light, released when the cosmos was still in its infancy. Today, the cosmic microwave background is observed as a faint glow at about 2.7 Kelvin because cosmic expansion stretched its wavelength over billions of years. Light that was once much hotter and more energetic has been stretched into microwave wavelengths by the expanding universe. So the background is both ancient and cooled by time and distance. It is one of the quietest and oldest signals that can still be measured. Dark matter and dark energy are inferred because observed cosmic behavior cannot be fully explained by ordinary visible matter alone. Galaxies rotate in ways that suggest extra unseen mass, and the expansion of the universe behaves as though another large-scale influence is present. Physicists use the names dark matter and dark energy to describe these effects, even though their exact nature remains uncertain. In this way, physics is honest about what it sees clearly and what it still does not understand. Dark matter appears through gravitational effects, while dark energy is associated with the universe's large-scale expansion behavior. Dark matter seems to act like extra gravity, helping shape galaxies and clusters, while dark energy is linked to the accelerated expansion of the cosmos. So they are not just two names for the same mystery. They point to different patterns in observation and different open questions in modern physics. Some of the biggest known ingredients of the cosmos are known more by their effects than by direct detection. This is a humbling feature of modern science. Sometimes the universe announces the presence of something not by showing it plainly, but by revealing how stars move, how light bends, or how space expands. Physics is often the art of learning from consequences when the cause itself remains hidden. Physics regularly turns abstract principles into tools, such as clocks, lasers, medical imaging, radio communication, and navigation systems. This is one of the most comforting things about the subject. Ideas that seem distant or mathematical often become useful in ordinary life. A law of nature can begin as a quiet insight and end as a device in a hospital, a phone, or a satellite system. The path from theory to technology is one of the great themes in physics. General relativity describes gravity not as a conventional force field alone, but as the curvature of space-time produced by mass energy. In this picture, massive objects do not simply pull on one another through empty space in the old intuitive sense. Instead, they shape the geometry of space-time around them, and other objects move along paths allowed by that curved geometry. It is a deeper and stranger way of understanding gravity, and it changed physics completely. Relativity begins from the idea that the laws of physics are the same in all suitable frames. That means nature does not secretly prefer one smoothly moving observer over another. If two observers move at constant speed relative to each other, the basic laws should still work for both. This principle sounds simple, but it leads to a dramatic reshaping of ideas about time, distance, and motion. Special relativity also takes the speed of light in vacuum as the same for all inertial observers. This is a radical statement because it means space and time must adjust so that this speed remains constant. As a result, measurements of time and length are not as absolute as they seem in everyday life. They depend on motion in ways that only become noticeable at very high speeds. From those principles come effects such as time dilation and length contraction. Time dilation means a moving clock can be measured as ticking more slowly relative to another observer, while length contraction means distances along the direction of motion can appear shorter. These are not illusions or mistakes, but real consequences of how space-time works. Though they are subtle in daily life, they become essential in high-speed physics. Mass and energy are related by the famous equation E equals mc2. This relationship means mass can be understood as a concentrated form of energy. The equation does not mean mass constantly turns into energy in ordinary objects, but it does mean the two are deeply connected at the fundamental level. It helps explain nuclear processes, particle physics, and the enormous energy available in matter itself. Relativity changed not only physics formulas, but the basic concepts of space and time. Before relativity, many people imagined time as universal and flowing the same for everyone, everywhere. After relativity, time became linked with space in a shared structure called space-time. This was not just a new calculation method, but a new vision of reality. Gravity is the force that attracts masses toward one another. In the older classical picture, gravity is a universal attraction that acts between all objects with mass. It is why apples fall, planets orbit, and galaxies hold together. Even though modern relativity provides a deeper description, the classical idea of gravitational attraction still works extremely well in many everyday and planetary situations. A satellite stays in orbit because it is constantly falling around Earth rather than straight down into it. If it has enough sideways speed, the curve of its fall matches the curve of Earth's surface. So it keeps missing the ground while still remaining under the influence of gravity. Orbit, in that sense, is a continuous fall guided into a graceful path. Orbital motion is one of the clearest examples of gravity producing continuous curved motion. Instead of pulling an object straight inward to a crash, gravity can bend its path into a stable loop or arc when the speed is right. This is why moons circle planets and planets circle stars. Motion and attraction together create the lasting geometry of orbits. The same gravitational principles that keep the moon in orbit also keep planets moving around stars. Physics is powerful because it does not need a different rule for every scale. The force that shapes motion in the Earth-Moon system also governs the architecture of solar systems. A single set of ideas can reach from nearby space to vast cosmic structures. Tides come from differences in gravity across an extended body, not just from gravity's overall pull. One side of Earth feels a slightly different gravitational effect than the other, and that difference stretches the oceans. This is why tides are more subtle than simply saying the moon pulls water upward. They are really about gradients in gravity acting across the whole planet. Near Earth's surface, gravity gives falling objects nearly the same acceleration regardless of their mass if air resistance is negligible. This often feels surprising because heavier objects seem as though they should fall faster. But in the absence of strong drag, gravity accelerates them nearly equally. It is one of the elegant simplifications that makes physics both powerful and beautiful. Freefall produces apparent weightlessness because the object and its surroundings accelerate together. In orbit, astronauts still live in Earth's gravity, but they and their spacecraft are falling together around the planet. Because nothing is pushing up on them in the usual way, they feel weightless. This is a subtle but important distinction between gravity being absent and weight seeming to disappear. The cosmic microwave background is one of the best probes of the early universe. Because it comes from such an ancient time, it preserves information about conditions long before stars and galaxies fully formed. Small variations in it reveal differences in density, temperature, and structure in the young cosmos. It is one of the most important data sources in modern cosmology. Measurements of the cosmic microwave background have shaped modern cosmology, including ideas about inflation and large-scale structure. By mapping its tiny variations, scientists can test models of how the universe expanded and how matter later gathered into galaxies and clusters. This is a case where delicate patterns in faint radiation carry enormous meaning. Small signals can answer very large questions. Tiny, early fluctuations in density grew under gravity into galaxies and clusters. The early universe was not perfectly smooth. It had slight differences from place to place, and gravity amplified those differences over time. From those tiny, irregular beginnings came the vast architecture of the visible cosmos. Modern large-scale cosmic structure is therefore connected to very small irregularities in the young universe. This is a beautiful example of how small beginnings can shape immense outcomes. The web of galaxies seen today can be traced back to subtle patterns in the early cosmos. Physics often links the largest visible structures to tiny initial differences. Physics near black holes and neutron stars tests matter and gravity in extreme conditions that cannot be reproduced easily on Earth. These objects act like natural laboratories where density, motion, magnetic fields, and gravity all reach extraordinary levels. By studying them, scientists can push theories into regimes far beyond ordinary experience. The universe, in this sense, performs experiments on a grand scale. NASA groups these topics under physics of the cosmos because the universe itself becomes a laboratory for extreme physics. Instead of building every experiment by hand, scientists can also observe nature's own most powerful environments. Supermassive objects, violent mergers, hot plasmas, and large-scale expansion all reveal how physical laws behave under stress. The sky is not only scenery, it is evidence. Extreme astrophysical objects help scientists study fundamental laws, not just exotic astronomy. A black hole or neutron star is not interesting only because it is strange. It is important because it tests whether our deepest ideas about matter, radiation, and gravity remain true in the harshest conditions. In that way, astronomy and fundamental physics often meet in the same place. Physics often progresses by connecting phenomena that once seemed unrelated, such as light and magnetism, or heat and microscopic motion. Again and again, the field becomes more powerful when separate ideas are discovered to be parts of one deeper pattern. This unifying tendency is one reason physics can describe so much with so few central principles. The story of the subject is often a story of hidden connections becoming clear. A single law can apply across enormous scales, from atoms in a lab to galaxies in the sky. This ability to stretch from the tiny to the immense is one of the most remarkable features of physics. The same logic used in controlled experiments can often illuminate distant cosmic systems. Few other human intellectual tools have such wide reach. Physics is both descriptive and predictive. It explains what happens and also tells engineers what should happen before they build something. That predictive power is why physics supports technology so effectively. It is not only a record of what nature has done, but a guide to what nature will do under carefully chosen conditions. This is why bridges, circuits, spacecraft, and detectors can be designed with confidence. The field keeps changing because each increase in precision can uncover new questions, even when old equations still work. A theory may remain accurate within known limits, yet sharper measurements can reveal tiny discrepancies or new domains where deeper ideas are needed. This means physics grows not only through dramatic revolutions, but also through quiet improvements in accuracy. Better measurement often leads to better understanding. The history of physics shows a repeated pattern in which better instruments make hidden aspects of nature measurable. Telescopes revealed distant worlds, microscopes opened smaller ones, and modern detectors uncover signals that were once completely inaccessible. In many cases, nature was always doing the same thing. Humans simply lacked the means to notice. Progress often begins when sensitivity improves. The universe supplies natural laboratories for extreme physics, while laboratories on Earth supply controlled tests of precise theories. These two approaches complement each other. Space offers scale, violence, and age beyond human construction, while earthly experiments offer repeatability and careful isolation. Together, they give physics both breadth and precision. Many modern technologies depend on quantum physics, electromagnetism, and relativity at the same time, even if users never notice. A person using navigation, communication, or advanced electronics may be relying on several deep physical theories at once. This hidden layering is part of what makes modern technology so extraordinary. Quiet scientific ideas sit inside ordinary devices. Physics remains unfinished because dark matter, dark energy, quantum gravity, and matter-antimatter asymmetry are still open problems. That incompleteness is not a weakness, but a sign of honesty and depth. The subject has achieved immense success, yet still faces some of the biggest questions imaginable. The unknown remains part of the landscape. Even with those mysteries, physics already provides one of humanity's most unified and experimentally tested descriptions of nature. It links motion, light, heat, matter, fields, atoms, stars, and the evolution of the universe in one broad framework. No theory set is complete, and no model is beyond improvement, yet the level of coherence already achieved is extraordinary. Physics is unfinished, but it is also profoundly successful. One of physics' central goals is to find patterns simple enough to describe many different phenomena with the same laws. This search for simplicity does not mean the universe itself is always simple in appearance. Instead, it means that underneath complexity, there may be a smaller number of reliable principles. Much of the beauty of physics lies in discovering those hidden underlying patterns. Modern physics is often organized into areas such as mechanics, thermodynamics, electromagnetism, quantum physics, relativity, nuclear physics, and particle physics. These branches are useful for study and teaching, but nature itself does not place firm walls between them. Real systems often draw from several at once. The categories help the mind, while the universe remains seamlessly connected. Physics studies matter, energy, motion, forces, and the rules that connect them. That scope is vast enough to include a swinging pendulum, a lightning storm, a laser, a galaxy, or a black hole. The subject is not just about objects, but about relationships and change. It asks what things are made of, how they move, and why they behave with such consistency. Some of the most powerful discoveries in physics are not new objects, but new symmetries, conservation laws, or measurement standards. Sometimes progress comes not from finding a new particle or phenomenon, but from recognizing a deeper rule that was always there. These abstract ideas can organize enormous amounts of knowledge. They become the quiet structure beneath many separate observations. Classical mechanics describes how large everyday objects move under forces. This is the branch of physics that helps explain the motion of cars, falling objects, swinging doors, bouncing balls, and planets moving through space when speeds are not extremely close to the speed of light. It gives us a reliable way to describe how position, speed, acceleration, and force are connected. Even though modern physics includes deeper theories, classical mechanics is still one of the most useful and practical frameworks ever developed, because so much of ordinary life follows it very closely. Newton's laws remain one of the main frameworks for understanding motion at ordinary speeds and sizes. His first law explains why objects keep doing what they are already doing unless something changes their motion. His second law connects force, mass, and acceleration in a precise mathematical way. His third law reminds us that forces come in pairs, with every action accompanied by an equal and opposite reaction. Together, these laws built a foundation that still supports engineering, transportation, construction, and much of everyday physical reasoning. A force changes motion by changing speed, direction, or both. If an object speeds up, slows down, or turns, then a force is involved somewhere. Sometimes that force is obvious, like a hand pushing a box. Sometimes it is less obvious, like gravity pulling downward or friction resisting motion. Physics pays close attention to these changes because motion by itself is not the whole story. What matters is how motion changes and what causes that change. Inertia is the tendency of an object to resist changes in its state of motion. A still object tends to remain still, and a moving object tends to keep moving in the same direction and at the same speed unless a force acts on it. Heavier objects feel harder to start or stop because they have more inertia. This is why a small empty cart is easier to push than a loaded one. Inertia is one of the quiet background ideas of mechanics, always present whenever motion begins, ends, or changes. The same laws that describe a rolling ball also help engineers predict spacecraft motion. That may seem surprising at first, because a ball on the ground and a spacecraft in orbit feel like very different things. But the same physical principles about motion, force, and momentum still apply. The details change, of course, especially because space has much less friction and much larger distances, but the underlying structure remains beautifully consistent. This is one reason physics is so powerful. The same laws can work across very different settings. Momentum combines mass and velocity, which is why a heavy, slow object and a light, fast object can sometimes be equally hard to stop. Momentum is not just about how much matter an object has, or only how fast it moves, but both together. That helps explain why a slowly moving truck may still carry a great deal of impact, and why a fast-moving baseball can hit with surprising force. In physics, momentum is one of the most useful ways to describe motion, especially when objects collide or push against one another. In a closed system, total momentum is conserved. This means that if no outside force significantly affects the system, the total amount of momentum before an interaction remains the same afterward. The momentum may be shared differently between objects, and individual objects may speed up, slow down, or reverse direction, but the total balance remains steady. This rule is especially useful in collisions, explosions, recoil, and orbital problems. It gives physics a dependable way to track what motion can and cannot happen. Conservation laws are among the most powerful ideas in physics because they limit what can happen before you calculate every detail. If energy, momentum, charge, or angular momentum must be conserved, then many impossible outcomes can be ruled out immediately. This saves enormous effort and gives deeper insight into how nature behaves. Conservation laws are like quiet rules in the background, guiding motion and change even when the force situation is complicated. They are part of the reason physics can stay elegant even when reality becomes messy. Angular momentum is conserved too, which is why spinning skaters rotate faster when they pull their arms inward. When the skater brings mass closer to the axis of rotation, the spin rate increases to preserve angular momentum. The same basic principle also shows up in rotating stars, spinning planets, and many machines. It is one of those wonderful examples where a simple movement in everyday life reflects a rule that also applies on very large scales. Rotation, like straight-line motion, follows deep conservation principles. Rotational motion has its own version of inertia, called moment of inertia, which depends on how mass is distributed around an axis. Two objects can have the same total mass, but behave very differently when spinning if their mass is arranged differently. If more mass sits farther from the axis, the object resists changes in rotation more strongly. This is why shape matters so much in spinning motion. Physics does not only ask how much matter there is, but also where that matter is placed. Weight is the force gravity exerts on a mass, while mass itself measures inertia. In everyday conversation, people often treat weight and mass as if they mean the same thing, but physics separates them carefully. Mass tells you how much an object resists acceleration. while weight tells you how strongly gravity is pulling on it in a specific place. This distinction becomes especially useful when comparing conditions on different worlds or when thinking about motion in space. Clear definitions make confusing situations much easier to understand. That distinction is why the same astronaut can have the same mass on the Moon and Earth but different weights. The astronaut's body does not lose matter during the trip, so the mass stays the same. But because the Moon's gravity is weaker than Earth's, the pull acting on that mass is smaller, so the astronaut weighs less there. This simple example helps show why physics keeps these two ideas separate. The difference is not just vocabulary, it reflects two different physical properties. Physics often becomes clearer when it separates related ideas that everyday language blends together. Words used in daily life are often broad and flexible, which is helpful in conversation but sometimes too loose for science. Physics becomes powerful by carefully distinguishing things like mass and weight, heat and temperature, speed and velocity, or energy and power. These distinctions allow more accurate thinking and better predictions. Often, scientific clarity begins when similar-sounding ideas are gently untangled. Friction is a force that resists relative motion between surfaces in contact. It can slow a sliding object, help tires grip the road, warm surfaces through rubbing, and make everyday movement possible. Friction is sometimes seen as a nuisance because it wastes mechanical energy as heat, but without it, many ordinary actions would fail. It is one of those forces that quietly shapes daily life all the time. Walking, writing, braking, and holding objects all depend on it. Without friction, walking would be much harder because your foot would slide backward instead of pushing the ground. When you walk, your foot presses backward against the surface, and friction allows the ground to push you forward. If there were no friction, you would struggle to gain traction and would slip easily. This shows that friction is not only something that opposes motion. In some situations, it is exactly what makes controlled motion possible. Air resistance is a form of drag caused by motion through a fluid. Even though air feels light and easy to move through at low speed, it still pushes back against moving objects. That resistance depends on shape, speed, and the properties of the air. It is why leaves drift, why cyclists lean forward, and why falling objects do not keep accelerating forever in the atmosphere. Drag is the fluid version of resistance, and it becomes more important as speed rises. Drag depends strongly on speed, which is why very fast motion through air becomes much harder to sustain. At low speed, air may feel like a minor detail, but as speed increases, drag can grow dramatically. This means that doubling speed can require much more than double the effort to keep going. That is why aerodynamic design matters so much in cars, airplanes, racing, and sports. Physics teaches that the medium around an object can matter as much as the object itself. Some forces oppose motion and some maintain it, so motion alone does not tell you which forces are present. An object moving steadily in a straight line does not necessarily have a force pushing it forward. Overall, the forces might simply balance out. In other cases, motion may continue because no strong opposing force is acting. This is one of the reasons physics moved beyond the old intuition that motion itself always requires a continuing push. What matters most is not motion alone, but whether motion is changing. Pressure is force spread over an area. If the same force is applied to a small area, the pressure is greater if it is spread across a larger area. The pressure is smaller. This idea helps explain why snowshoes keep a person from sinking as deeply, why needles pierce effectively, and why large machinery can still damage a surface if enough force is concentrated. Pressure is a simple concept, but it appears everywhere in fluid systems, engineering, weather, and everyday contact between objects. A sharp blade cuts well because the same force is concentrated onto a much smaller area. The narrow edge increases pressure dramatically, making it easier for the material being cut to separate. This is not because the blade somehow creates more force, but because it uses the force more efficiently by focusing it. Physics often shows that effectiveness depends not only on quantity, but on distribution. Where a force acts can matter just as much as how large it is. Fluids transmit pressure in ways solids do not, which is why hydraulics can amplify force. In a hydraulic system, pressure applied in one place can be carried through a fluid and used somewhere else. Because the fluid transmits pressure efficiently, a small force on a small piston can help create a much larger force on a larger piston. This principle is used in car brakes, lifts, heavy machinery, and many tools. It is a beautiful example of how fluid behavior can be turned into practical power. Buoyancy occurs because pressure in a fluid increases with depth, producing a net upward force on submerged objects. The bottom of an object in a fluid feels more pressure than the top, and that difference creates an upward push. This is why objects can float, sink, slowly, or feel lighter underwater. Buoyancy is not magic or mystery, but a direct consequence of how pressure changes inside fluids. It turns a simple pressure gradient into a force that can hold up ships and swimmers. Floating depends on density and displaced fluid, not on whether something looks heavy. A large steel ship may seem far too heavy to float, yet it can float because its overall average density, including the air inside it, can be less than that of water. What matters is how much fluid is displaced and whether the buoyant force can balance the weight. Physics often corrects first impressions in this way. Appearance can mislead, while density and force balance tell the true story. Density is mass per unit volume. It tells us how tightly matter is packed into a given space. Two substances of the same size can feel very different in the hand because one contains much more mass in that volume. Density helps explain floating, sinking, material choice, planetary structure, and many natural processes. It is one of the simplest measurements in physics, but it carries a great deal of information. Two objects can have the same mass but very different densities if one occupies much more space. Imagine a kilogram of metal and a kilogram of foam. Their masses are equal, but the foam spreads that mass over a much larger volume, so its density is lower. This difference affects how they float, how they feel, and how they behave in physical systems. Density is a reminder that mass alone does not tell the whole story about matter. Center of mass is the balance point of an object or system. If you could support the whole object exactly at that point, it would balance in every direction. For simple objects, the center of mass may sit in the obvious middle, but for irregular shapes, it can be somewhere unexpected. In multi-object systems, it depends on how all the masses are arranged together. This concept is useful in mechanics, sports, engineering, and motion analysis because balance and movement often depend on it. Stability often depends on whether the center of mass stays above the support area. If the center of mass shifts too far outside that base, the object is likely to tip over. This is why wide stances can feel more stable, why tall, narrow objects are easier to topple, and why carrying a load high up can make walking feel less secure. Physics explains stability with surprisingly simple geometry. Balance is often less about strength than about where the mass is located. Many everyday balance problems are really center-of-mass problems in disguise. A ladder leaning against a wall, a person carrying groceries, a chair tipping backward, or a gymnast holding a pose, all involve the distribution of mass relative to support and motion. Once the center of mass is understood, many situations that seemed complicated become much clearer. This is a common gift of physics. Hidden behind ordinary experience is often one clean, organizing idea. A pendulum swaps energy back and forth between gravitational potential energy and kinetic energy. At the highest points of its swing, it has more gravitational potential energy and less motion. At the lowest point, more of that energy has been converted into kinetic energy, so it moves fastest there. Then the process reverses as it rises again. A pendulum is a calm and visible example of energy transformation happening in a steady rhythm. Small pendulums swing with a period that depends mainly on their length and local gravity. That means the time for one full swing is not strongly controlled by how heavy the bob is, at least for small swings. Longer pendulums take more time, while stronger local gravity shortens the period. This made pendulums very useful in timekeeping for many years. It also shows how motion can reveal hidden information about environment and structure. Jean Foucault used a pendulum in 1851 to demonstrate Earth's rotation in a laboratory setting. This was a striking achievement because it allowed people to witness the planet's rotation, not by looking at the sky, but by observing a carefully prepared system in one room. The pendulum itself did not need to circle the Earth or go into space. Instead, Earth turned beneath it, and the pattern of swing revealed that motion. It was a local experiment with a global meaning. A Foucault pendulum's plane of swing appears to rotate because Earth turns underneath it. From the pendulum's point of view, it keeps swinging in nearly the same plane. But from the perspective of someone standing on the rotating Earth, the direction seems to shift over time. The amount and rate of this turning depend on latitude. It is one of the most elegant demonstrations in physics because it turns something slow and gentle into evidence for the motion of an entire planet. Physics sometimes reveals global facts about a planet using only a local experiment in one room. This is part of what makes the subject so satisfying. A carefully designed setup can connect nearby motion to large-scale truths. The Foucault pendulum is one example, but the broader lesson is even more powerful. Nature's rules link local measurements to vast realities. A room can become a window into the Earth. Energy is the capacity to produce change, and it appears in many forms. It can be carried by motion, stored in position, transferred by heat, held in electric fields, released in chemical reactions, or locked into mass. The idea of energy is so important because it gives one common language for describing many different processes. Instead of treating every change as a completely separate event, physics can track how energy moves and transforms across different systems. Kinetic energy is associated with motion. The faster something moves, the more kinetic energy it has, and the amount also depends on its mass. A heavy object and a fast object can both carry substantial kinetic energy, though in different ways. This idea helps explain why moving vehicles require careful stopping distances, why winds can do work, and why impacts can be powerful. Motion is not only movement through space, it is also stored capacity for change. Potential energy is associated with configuration, such as position in a gravitational field or the stretching of a spring. It is energy stored because of arrangement rather than present motion. A raised object, a compressed spring, or separated electric charges can all hold potential energy. When conditions change, that stored energy can be released and turned into motion or other forms. Physics often finds that stillness is not emptiness. It may simply be stored possibility. In closed systems, total energy is conserved even when it changes form. Energy may shift from motion to heat, from potential to kinetic, from electrical to light, or from one system to another, but it does not simply vanish. This principle is one of the deepest and most reliable in science. It gives physicists a way to follow change through many different processes. Even when the visible form changes completely, the total balance remains. Conservation of energy is one of the deepest organizing principles in all of physics. It applies across mechanics, thermodynamics, electricity, waves, chemistry, and modern physics. The exact bookkeeping can be subtle, especially in complicated systems, but the overall rule remains one of the most trusted guides available. It is one of the reasons physics can unite many different branches under one broad structure. The forms may vary, but energy remains a common thread. Mechanical energy can transform into heat through friction. When surfaces rub, some of the organized motion is converted into microscopic motion among particles, which we experience as warming. This is why your hands become warm when rubbed together, and why brakes heat up during use. The original mechanical motion is not lost without explanation. It simply changes form. Physics often explains familiar experiences by showing where the energy went. Heat is energy transferred because of the temperature difference. If one object is warmer than another, energy tends to flow from the warmer one to the cooler one. That transfer is what physics calls heat. This is important because heat is not the same as something stored inside an object in a vague way. It specifically refers to energy in transit due to temperature difference. Clear language helps keep thermal ideas from becoming confusing. Temperature is not the same thing as heat. Temperature tracks the average microscopic energy distribution, while heat is transfer. Temperature tells us something about the state of particles in a system, especially their average energetic behavior, while heat refers to energy moving from one place to another because of a difference in temperature. This distinction is one of the most important in thermodynamics. It helps explain why a tiny spark can have a very high temperature but contain little total thermal energy. Two objects can contain very different amounts of total thermal energy, even if they share the same temperature. A small cup of hot water and a large bathtub of water at the same temperature do not contain the same total amount of thermal energy. The bathtub has much more matter at that temperature, so the total energy involved is far greater. This shows why temperature alone cannot tell the whole thermal story. Size and amount of material matter too. Physics becomes more precise when it distinguishes stored quantities from transferred quantities. That is why it carefully separates ideas like energy from power, mass from weight, and temperature from heat. Stored quantities describe what a system has, while transferred quantities describe what is moving between systems or how quickly change occurs. This habit of careful distinction is one of the reasons physics can stay both subtle and reliable. Precision in language supports precision in thought. Thermodynamics studies energy, work, heat, and the direction of physical processes. It asks not only how much energy is involved, but how it flows, what forms it takes, and why some changes happen naturally while others do not. Thermodynamics is essential in engines, refrigeration, weather, chemistry, biology, and daily life. It is one of the great bridges between microscopic behavior and large-scale experience. Through it, warm tea cooling on the table and power plants generating electricity become part of the same broad story. The first law of thermodynamics is a statement of energy conservation applied to thermal systems. It says, in essence, that energy is not created or destroyed in these processes, but changes form or moves between systems. Heat added to a system can increase internal energy or be used to do work, and work done on a system can affect its thermal state. This law is the thermal version of a much deeper truth in physics. It keeps the bookkeeping honest. The second law explains why some energy transformations happen naturally in one direction more readily than the reverse. Heat tends to flow from warmer objects to cooler ones on its own, not the other way around. Cream mixes into coffee more naturally than it unmixes. Orderly energy often spreads into less concentrated forms. The second law does not say reverse changes are absolutely impossible in every tiny detail, but that the overall direction of natural processes strongly favors certain outcomes. Entropy is a key concept for describing that directionality. It is often used to describe how energy becomes more spread out, or how many microscopic arrangements fit a large-scale state. Entropy helps explain why some changes are easy and common, while others are technically possible but overwhelmingly unlikely. It is not simply disorder in a casual sense, though that can sometimes be a rough starting intuition. In physics, entropy is a careful way of describing the direction built into many real processes. Many processes are possible in principle but unlikely in practice because they would require entropy to decrease overall. For example, the molecules in a room could in theory all gather into one corner by random motion, but the odds are so tiny that it never happens in any practical sense. Physics distinguishes between what the laws technically allow and what is realistically expected. This is why thermodynamics feels so solid in daily life. The improbable is not forbidden, but it is effectively absent. Entropy is often associated with the number of microscopic arrangements compatible with a macroscopic state. A large-scale situation such as a gas spread evenly through a box can be realized by an enormous number of tiny particle arrangements. A more special arrangement, like all the gas crowded into one small region, corresponds to far fewer possibilities. Because systems naturally explore what is statistically available, high-entropy states are much more common. This gives entropy a deep connection to probability as well as physical change. Warm objects placed next to cool ones tend to move toward a common temperature because that usually increases total entropy. Energy spreads from the warmer object into the cooler one until the difference becomes smaller and eventually disappears. This is why hot drinks cool down and cold objects warm up when left in a room. The process feels ordinary because it is so familiar, but thermodynamics explains why it happens with such consistency. Nature tends towards shared balance when energy can spread. A refrigerator does not violate thermodynamics because it uses external work to move heat from cold to warm surroundings. Left alone, heat would naturally flow the other way. The refrigerator overcomes that natural direction by consuming electrical energy and using a carefully designed cycle to pump heat outward. So it is not cheating the laws of physics, it is working within them by paying an energetic cost. This is one of the most practical examples of thermodynamics in everyday life. Phase changes such as melting and boiling involve latent heat, which means energy can be added or removed without the temperature necessarily changing at that moment. Instead of making particles move faster right away, that energy can go into changing how they are arranged or how strongly they are bound together. This is why ice can keep melting at the same temperature until the change of state is complete. Physics shows that energy is not always used to make something hotter in the usual sense. Sometimes it is used to reorganize matter itself. Boiling depends on pressure as well as temperature, which is why water boils at lower temperatures at high altitude. Boiling happens when the pressure of vapor inside the liquid can match the pressure pushing down on it from outside. When the surrounding pressure is lower, that balance is reached sooner, so the liquid can boil at a lower temperature. This is why cooking can change in mountainous places. A simple pot of water is quietly responding to the physics of the atmosphere around it. Heat capacity measures how much energy is needed to raise a substance's temperature. Some materials warm quickly when energy is added, while others need much more energy to change by the same amount. Heat capacity helps describe that difference in a precise way. It is one of the reasons metal, water, air, and stone can all respond so differently to the same heating. Physics often explains everyday sensations by showing that materials do not all store and respond to energy in the same manner. Specific heat is heat capacity per unit mass. This makes it easier to compare different substances fairly, because it tells us how much energy is needed to raise the temperature of a standard amount of material. A kilogram of one substance may need much more energy to warm than a kilogram of another. This is useful in climate, engineering, cooking, and energy systems. It turns a broad idea about warming into a clear material property. Water's high specific heat is one reason it moderates temperature changes in nature and daily life. Because water can absorb or release a large amount of energy without changing temperature too quickly, it helps stabilize environments. Oceans, lakes, and even the water in living bodies benefit from this gentle buffering effect. This property is one reason coastal climates are often milder than inland climates. A simple physical property of water quietly shapes weather, biology, and comfort. Thermal expansion happens because average particle spacing changes as temperature changes. When a material warms, its particles usually move more energetically and tend to spread slightly farther apart on average. That change may be very small at the microscopic level, but in large objects it can become important. Bridges, rails, pipes, and buildings all need to account for expansion and contraction. Physics reminds us that even solid-looking structures are always responding to temperature. Solids, liquids, and gases generally expand when heated, though the exact behavior depends on structure. The effect is usually strongest in gases, more moderate in liquids, and often smaller in solids, but each material has its own details. Some substances even behave in unusual ways over certain temperature ranges. This means engineers cannot assume all matter responds identically to heating. The broad rule is simple, but the specific response belongs to the internal structure of the material. Pressure, volume, and temperature are linked in gases, which is why heating a confined gas raises its pressure. If the gas cannot expand, the faster motion of its particles leads to more forceful and frequent collisions with the walls of the container. That increased microscopic activity appears as higher pressure. This connection is central to engines, weather, containers, and many laboratory systems. Gas laws translate invisible particle motion into measurable large-scale behavior. Ideal gas behavior is an approximation that works best when particles are far apart and interactions are weak. In this simplified model, the particles are treated as tiny objects moving around and colliding without strong attractions or repulsions most of the time. Real gases do not behave perfectly this way under all conditions, especially when pressure is high or temperature is low. Still, the ideal gas picture is often accurate enough to be extremely useful. Physics frequently begins with simple models that capture the main behavior before adding complexity. Statistical physics connects these large-scale thermodynamic laws to the motion of countless microscopic particles. Instead of tracking every particle one by one, which would be practically impossible, it uses averages, probabilities, and enormous numbers to explain bulk behavior. This is how ideas like temperature, pressure, and entropy gain a microscopic foundation. It shows that large-scale smooth behavior can emerge from tiny motions that are individually chaotic. A calm gas law can be the result of trillions of restless collisions. Waves transfer energy and information without requiring the bulk transport of matter from source to receiver. In a wave, the pattern moves while the material often only oscillates locally. A ripple across water is a familiar example. The disturbance travels outward, but the water itself mostly moves up and down rather than flowing across the whole pond with the ripple. This idea is central to sound, light, earthquakes, and communication. Physics uses waves to describe how change can travel through space and materials. A wave is characterized by properties such as wavelength, frequency, amplitude, and speed. These quantities give a structured way to describe how the wave behaves. Wavelength tells us the spacing of repetition, frequency tells us how often oscillation happens, amplitude tells us the size of the disturbance, and speed tells us how quickly the pattern moves. Together they form a basic language for wave behavior. Once these are understood, many very different wave phenomena begin to look related. Frequency counts how many oscillations occur per second. It is measured in hertz, where 1 hertz means 1 cycle each second. High frequency means rapid repetition, while low frequency means slower repetition. Frequency matters in music, radio, light, atomic clocks, and countless other systems. It is one of the clearest examples of how time enters into the description of repeating physical behavior. Wavelength is the distance between repeating points on a wave. For example, it may be measured from one crest to the next crest, or from one compression to the next. Wavelength helps tell us how stretched out or tightly packed the wave pattern is in space. In many systems, wavelength and frequency are related through the wave speed. This makes wavelength a bridge between the geometry of a wave and its timing. Amplitude measures the size of an oscillation and often relates to the wave's intensity. A larger amplitude usually means the wave carries more energy, though the exact relationship depends on the type of wave. In sound, amplitude is linked to how loud a sound may seem. In light, it relates to intensity or brightness. Amplitude is a reminder that waves are not only about pattern and timing, but also about strength. Sound is a mechanical wave and needs a medium such as air, water, or solid material to travel. It works through compressions and rarefactions moving through matter, which means there must be particles available to pass the disturbance along. Without a medium, sound has nothing to push and pull on. This is why sound behaves differently in air, water, and metal. Its journey depends completely on the material carrying it. Light is an electromagnetic wave and can travel through vacuum. Unlike sound, it does not need air, water, or any material medium in order to keep going. Its oscillating electric and magnetic fields sustain one another as the wave moves forward. This is why sunlight can cross the emptiness of space and still reach Earth. The ability of light to travel through vacuum is one of the deepest differences between electromagnetic and mechanical waves. This difference is why you can see the sun through space but cannot hear it through space. Light from the sun can travel across the vacuum between the sun and Earth, but sound cannot make that journey because there is no continuous material medium in open space to carry it. This simple contrast captures a very important physical principle. Two forms of energy transfer may both feel familiar, yet they obey very different rules. Physics often becomes memorable through contrasts like this. The speed of sound depends on the medium, while the speed of light in vacuum is fixed. Sound travels faster in some materials than in others because the particles and their interactions determine how quickly a mechanical disturbance can move through them. Light, in contrast, has a special fixed speed in empty space that does not vary from one vacuum region to another. This distinction separates a medium-dependent phenomenon from a fundamental constant of nature. It is one of the reasons light plays such a special role in physics. The nature of the medium matters deeply for mechanical waves, and not in the same way for electromagnetic waves. In sound, the material's density, elasticity, and structure strongly affect the wave's motion. In light traveling through vacuum, there is no material medium to define the propagation. Even when light passes through matter, it behaves differently from a mechanical wave because it is not simply pushing particles back and forth in the same direct way. This difference helps explain why wave physics contains both shared concepts and important separations. Reflection occurs when a wave bounces off a boundary. The wave reaches a change in medium or surface and turns back rather than continuing straight through. Reflection can happen with sound, water waves, light, and many other disturbances. Echoes, mirrors, and many signal effects all depend on it. It is one of the simplest and most universal wave behaviors. For light, the angle of incidence equals the angle of reflection. This means the incoming path and outgoing path are arranged in a very precise geometric way relative to the surface. It is one of the most basic rules in optics and helps explain how mirrors form predictable images. The rule is simple enough to learn quickly, yet powerful enough to design instruments with. A neat bit of geometry becomes a law of light behavior. Refraction occurs when a wave changes speed while entering a new medium, causing its path to bend. When part of the wavefront slows down or speeds up before the rest, the whole wave changes direction. This is why a straw can appear bent in water and why lenses can focus light. Refraction is not a random distortion, but a consequence of changing wave speed. It is one of the main ways light can be guided and shaped. Lenses work by controlled refraction. Their curved surfaces are designed so that light bends in useful ways, allowing it to converge, diverge, magnify, or form images. Glasses, cameras, microscopes, telescopes, and many scientific devices all depend on this principle. A lens does not create light or force it to change mysteriously. It simply uses the wave's response to new material conditions in a carefully planned way. Many optical devices are really carefully engineered systems for redirecting light through reflection and refraction. Mirrors, lenses, prisms, coatings, and layered materials all help control where light goes and how it behaves. The success of these devices depends on understanding light as something lawful and predictable. Instruments that seem magical often rest on very simple rules applied with great precision. Optics is one of the clearest examples of elegant physical control. A rainbow forms when sunlight interacts with water droplets through refraction, reflection, and dispersion. Light enters the droplet, bends, reflects inside, and bends again as it exits. Because different wavelengths bend by slightly different amounts, the colors separate. What seems like a soft sky decoration is actually the result of several optical processes working together. A rainbow is a delicate pattern created by geometry, light, and countless tiny droplets. The most familiar primary rainbow appears near a viewing angle of about 42 degrees. This angle is not arbitrary. It comes from the geometry of how light travels through the droplets and emerges back toward the observer. That is why the rainbow appears in a predictable relation to the sun and the observer's position. The beauty of it does not come from randomness, but from precise optical structure. Rainbows are not fixed objects in one location. Each observer sees light from different droplets. This means the rainbow you see is not exactly the same rainbow seen by someone standing elsewhere. Each person receives light from a slightly different set of droplets arranged at the correct viewing angle. So the rainbow is not like a painted arch sitting in the sky. It is more like a personal geometric pattern formed between sunlight, water, and the observer. Rainbows can also appear in fog, sea spray, or waterfalls. The essential requirement is not specifically rain, but many tiny droplets arranged so that light can refract, reflect, and disperse in the right way. This is why rainbow-like effects can appear in many natural settings beyond storms. Physics reveals the common rule behind what might otherwise seem like separate phenomena. The same optical process quietly repeats wherever conditions allow. A familiar sky phenomenon turns out to be a geometry problem involving light paths and droplet optics. This is one of the charming features of physics. Something emotionally simple and visually beautiful can also be described with precision, angles, and wave behavior. Explaining it does not make it less beautiful. Instead, it adds another layer of appreciation by showing how order and beauty meet. Dispersion happens because different wavelengths of light refract by slightly different amounts in a medium. In many transparent materials, shorter and longer wavelengths do not all slow by exactly the same amount. As a result, white light can spread into its component colors. This effect is essential in rainbows, prisms, and many optical systems. It shows that color is not only a visual experience, but also a measurable physical difference in wavelength. Spectroscopy studies light by separating it into wavelengths. Once light is spread out into its components, scientists can analyze patterns that reveal physical information about the source or the material the light passed through. This makes spectroscopy one of the most powerful tools in science. It can be used in laboratories, medicine, chemistry, and astronomy. By studying light carefully, scientists can learn about things they may never touch directly. Atoms and molecules leave characteristic patterns in spectra. Their internal energy structures allow them to absorb or emit only certain wavelengths under given conditions. Because those patterns are specific, they act like signatures. This allows scientists to identify materials by the light they interact with. Spectra turn invisible microscopic structure into something that can be observed and compared. Absorption spectra show dark lines where certain wavelengths are removed. When light passes through a material, some wavelengths may be absorbed because they match allowed energy changes in the atoms or molecules there. The missing wavelengths show up as dark gaps in the spectrum. These gaps carry valuable information about composition and physical state. In this way, absence becomes evidence. Emission spectra show bright lines where excited material emits specific wavelengths. When atoms or molecules release energy, they do not emit just any wavelength at random. They emit light at particular wavelengths tied to their energy level structure. These bright lines can be used to identify substances and understand physical conditions. It is a wonderfully direct way that quantum behavior becomes visible. Astronomers use spectroscopy to identify the composition, motion, and temperature of distant objects. Since stars and galaxies are too far away to sample directly, light becomes the messenger carrying their properties to us. By reading spectra, scientists can tell what elements are present, whether an object is moving, and often how hot or energetic it is. This is one of the great triumphs of physics, learning about distant places through patterns of light alone. Spectroscopy turns starlight into information. A Doppler shift changes observed wavelength when a source moves toward or away from an observer. If the source approaches, the waves are compressed in the direction of travel. If it recedes, they are stretched. This alters the observed frequency or wavelength without requiring the source itself to change what it emits. The Doppler effect is one of the most important ways motion can leave a measurable signature in waves. It connects movement directly to observation. Approaching sources shift toward shorter wavelengths, while receding sources shift toward longer wavelengths. In light, this is often described as a move toward the blue or toward the red part of the spectrum, though the exact wavelengths involved may not always be visible. The same principle appears in sound as a higher or lower pitch from moving sources. The direction of motion changes the pattern received. Physics uses that shift to read movement from a distance. The Doppler effect applies to both sound and light. A passing siren changes pitch as it moves relative to you, and starlight changes wavelength if a star or galaxy moves relative to Earth. The same underlying idea works across very different systems. This is one of the strengths of physics. Once a pattern is understood in one context, it often returns in another. A street sound and a galaxy can obey the same wave principle. The same underlying wave principle helps explain passing sirens, spacecraft tracking, and galaxy motion. Engineers use Doppler methods to measure speed. Astronomers use them to study cosmic motion, and everyday listeners notice them when vehicles pass by. What unites these examples is the way motion changes the arriving wave pattern. This makes the Doppler effect both highly practical and deeply universal. One clean idea reaches from ordinary roads to deep space. Electromagnetic radiation consists of interacting electric and magnetic fields that sustain each other as they travel. These fields oscillate together in a self-propagating pattern, allowing the wave to move through space. This is the physical structure behind radio waves, visible light, X-rays, and more. What seems like a wide variety of separate things is actually one family of related phenomena. Physics often reveals unity beneath variety. The electromagnetic spectrum runs from radio waves to gamma rays. The different regions are classified mainly by wavelength or frequency, not by being completely different kinds of substance. Radio waves have long wavelengths and low frequencies, while gamma rays have very short wavelengths and very high frequencies. Between them lie microwaves, infrared, visible light, ultraviolet, and X-rays. This vast spectrum shows how wide the family of electromagnetic radiation truly is. Visible light is only a small part of that spectrum. Human vision samples a narrow window, shaped by biology and the environment in which life evolved. There is much more electromagnetic activity outside what our eyes can directly detect. Physics extends perception by building instruments sensitive to those other bands. In that way, science lets human beings observe far beyond the limits of ordinary senses. Different wavelengths interact with matter in different ways. Some pass through certain materials easily, some are absorbed strongly, some can heat matter efficiently, and some can reveal fine structural details. This is why different parts of the spectrum are useful for different technologies and sciences. Radio waves communicate, infrared senses heat, visible light supports sight, and X-rays reveal interior structure. The behavior of matter depends strongly on the wavelength encountering it. Much of modern science depends on seeing the universe in wavelengths human eyes cannot detect. Telescopes and detectors sensitive to radio waves, infrared, ultraviolet, X-rays, and other bands reveal features of the cosmos that visible light alone would hide. Different wavelengths show different temperatures, materials, motions, and energetic processes. This means the universe has many layers of appearance depending on how it is observed. Physics enlarges vision by translating the invisible into knowledge. Electric charge comes in positive and negative forms. These two kinds of charge are fundamental to electricity and many interactions in matter. Their behavior is simple in one sense and very rich in another. Opposite charges attract, like charges repel, and that basic rule drives countless physical systems. From atoms to circuits, charge helps organize structure and motion. It is one of the key ingredients of electromagnetic physics. Like charges repel and unlike charges attract. This rule may sound basic, but it has enormous consequences. It helps explain the structure of atoms, the behavior of currents, static electricity, chemical bonding, and the design of electrical systems. The same law that makes rubbed objects cling or spark also helps shape matter on very small scales. A very simple interaction pattern can support a huge amount of physical complexity. Electric current is the flow of charge. In many everyday circuits, this means electrons moving through a material, though the full story depends on the system involved. Current is not just electricity in a vague sense, but a specific rate of charge movement. This allows it to be measured, controlled, and used to transfer energy. The concept is simple, yet it supports the operation of modern electronics and power systems. Voltage describes electric potential difference, which can drive charge through a circuit. It is often helpful to think of voltage as the push that encourages charges to move, though the full picture is more precise than that analogy. Without a potential difference, current generally does not flow in the same useful way. Voltage, current, and resistance together form a central trio in circuit physics. They give electrical systems a clear structure for analysis. Resistance measures how strongly a material opposes current flow. Some materials allow charge to move easily, while others hinder it more strongly. Resistance affects heating, power use, efficiency, and the design of electrical devices. It depends on the material, shape, temperature, and other conditions. In electrical physics, resistance is the quiet control that keeps current from behaving the same way everywhere. Ohm's law relates voltage, current, and resistance in many simple circuits. In its most familiar form, it says that current depends on voltage divided by resistance. This gives a clean way to understand why more voltage can drive more current, while greater resistance can reduce it. It is not a universal law for every material under all conditions, but for many ordinary electrical situations, it works very well. Because of that, it became one of the first and most important tools for understanding circuits. Power in an electrical system describes how fast energy is transferred. It tells us not just that energy is moving, but how quickly that movement is happening. A small device and a large machine may both use electricity, but their power levels can be very different because one transfers energy much faster than the other. This helps explain why some devices run gently and others produce strong heating, motion, or light. In physics, rate matters, and power is the rate of energy use or delivery. Static electricity results from an imbalance of charge rather than a continuous current. Charges can build up on surfaces when materials rub together or separate, and then remain there until they discharge. That is why a person can feel a sudden spark after walking across a carpet or removing certain clothing. The effect can seem surprising, but it comes from charge accumulation, not from the steady flowing current seen in ordinary powered circuits. It is electricity in a stored, not continuously moving form. Capacitors store energy in electric fields. They do this by holding separated charges in a way that creates a field between them. Even though the charges do not simply rush together immediately, the arrangement stores usable energy that can later be released into a circuit. Capacitors are important in timing, filtering, smoothing electrical signals, and many other tasks in electronics. They show that electrical systems can store energy not only chemically, like batteries, but also directly in fields. Inductors store energy in magnetic fields. When current flows through an inductor, a magnetic field forms around it, and energy is held in that field. Because of this, inductors resist sudden changes in current, making them useful in many types of electrical and electronic systems. They are common in transformers, filters, power supplies, and communication devices. Inductors remind us that electricity and magnetism are not separate worlds, but closely linked parts of one deeper framework. Magnetism is produced by moving charges and by intrinsic magnetic properties of particles. A current in a wire creates a magnetic field, and certain particles, such as electrons, also possess magnetic behavior as part of their quantum nature. This means magnetism is not a separate, mysterious substance, but a feature of charge and motion at both large and small scales. From refrigerator magnets to planetary fields and particle physics, magnetic effects appear in many forms. Physics connects them through one broad electromagnetic picture. A current-carrying wire creates a magnetic field around itself. This is one of the most direct demonstrations of the connection between electricity and magnetism. If charge flows through a conductor, the space around that conductor becomes magnetically active in a predictable pattern. The effect is not only a laboratory curiosity. It is the working principle behind many technologies. including electromagnets, motors, and sensing devices. A simple wire carrying current becomes more than a path for charge. It becomes a source of field structure in space. Electromagnets use this link between electricity and magnetism to create controllable magnetic fields. Unlike permanent magnets, electromagnets can often be switched on, switched off, or adjusted in strength by changing the current. That makes them extremely useful in industry, medicine, transportation, and research. Cranes that lift metal, MRI systems, and many laboratory instruments depend on them. They are a beautiful example of how a fundamental physical principle becomes a flexible tool. Electric motors and generators rely on the same deep relationship, but in opposite operational directions. Motors use electric energy to produce motion, while generators use motion to produce electric energy. Both depend on the way magnetic fields and moving charges influence one another. This symmetry is one of the elegant features of electromagnetism. It shows that the same principle can be used to convert energy in either direction depending on how the system is arranged. Much of electrical technology exists because changing electric and magnetic fields can influence each other. This mutual relationship lies at the heart of transformers, radio transmission, induction systems, and electromagnetic waves themselves. A changing electric field can help create a magnetic field, and a changing magnetic field can help create an electric field. That interplay is not a small detail, but one of the central ideas of modern physics. It is part of what makes electromagnetism so rich and powerful. Electromagnetic waves transport energy through space without needing matter to carry them. This is why radio signals, sunlight, and many other forms of radiation can cross empty space. The wave is made of changing electric and magnetic fields rather than vibrations of a material medium. That feature sets electromagnetic waves apart from sound waves. It also makes them essential for communication, astronomy, and much of modern technology. Radio communication depends on controlled production and detection of electromagnetic waves. A transmitter creates patterns in electromagnetic radiation, and a receiver detects and interprets those patterns. What may feel like invisible magic is really a carefully organized wave process. Information rides on the wave through methods such as modulation, allowing sound, data, or signals to travel across great distances. Physics makes communication possible by turning field behavior into a language. Microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all part of one continuous family. They differ mainly in wavelength and frequency, not in belonging to completely separate categories of nature. This means the differences among them are differences of scale and interaction, not of fundamental identity. A kitchen microwave, a red sunset, and a medical X-ray all belong to the same broad electromagnetic story. Physics often reveals unity where everyday experience suggests separation. The human eye samples only a narrow wavelength window because biology evolved around solar conditions at Earth's surface. Our vision is not a complete detector for all radiation, but a specialized system tuned to one useful band. This makes sense for survival and daily life, but it also means human senses leave most of the electromagnetic spectrum unnoticed. Science expands that narrow window by building instruments that respond where eyes cannot. In this way, physics extends the reach of perception. Physics treats these diverse bands as variations of the same phenomenon rather than different substances. That way of thinking is one of the strengths of the subject. Instead of building unrelated explanations for radio, light, and X-rays, physics places them into one structured framework. This allows ideas discovered in one part of the spectrum to inform understanding in another. Unity of description is one reason electromagnetism is such a successful theory. Semiconductors sit between conductors and insulators in how easily they let charge move. They do not allow charge to flow as freely as metals, but they are not as resistant as strong insulators either. This middle behavior is what makes them so useful. A material that is not too open and not too closed can be controlled in subtle ways. That controllability is the foundation of much of modern electronics. Their behavior can be tuned by impurities, structure, and electric fields. Small changes in composition or conditions can greatly affect how charge moves through a semiconductor. This means engineers can design materials and devices that behave in highly specific ways. The ability to tune response is much more useful than having a material with only one fixed behavior. Physics often becomes technologically powerful when nature offers something adjustable rather than rigid. That tunability is why semiconductors are central to modern electronics. Transistors, chips, sensors, and countless digital systems depend on materials whose charge behavior can be carefully controlled. Modern computing would look completely different without semiconductor physics. What makes these materials valuable is not merely that they conduct somewhat, but that they can be switched, amplified, and organized into complex functions. A carefully managed flow of charge became the basis of the information age. Lasers produce light that is unusually directional and narrow in frequency. Unlike ordinary light sources, which often emit over many directions and many wavelengths, lasers can be highly focused and very regular. This makes them useful for communication, measurement, surgery, manufacturing, scanning, and scientific experiments. The word laser has become familiar, but the physics behind it is remarkably precise. It is one of the clearest cases where quantum and optical ideas combine to make a powerful tool. Optical fiber communication depends on carefully guiding light through transparent materials with low loss. The light is kept inside the fiber by internal reflection and related optical design, allowing signals to travel long distances while remaining readable. This makes it possible to send enormous amounts of information rapidly across cities, countries, and oceans. Modern communication networks rely heavily on this technology. A thin strand of material becomes a pathway for light-based information. Matter is commonly described in phases such as solid, liquid, gas, and plasma. These categories help organize the many ways matter can behave. Each phase has characteristic patterns of particle arrangement and motion. While the categories sound simple, they already capture a great deal about how matter responds to shape, flow, temperature, and pressure. Physics begins with these broad states and then explores the details within them. The main difference among these phases is how particles are arranged and how freely they move. In a solid, particles are typically held in relatively fixed positions. In a liquid, they remain close together, but can move past one another. In a gas, they move much more freely and spread out widely. Plasma adds the further feature of ionization, where electrons are no longer bound in the same way. So phase is really a story about microscopic organization and freedom of motion. Solids resist shape changes because their constituents are bound in relatively fixed structures. The particles in a solid usually vibrate around stable positions rather than roaming freely. This gives solids their familiar rigidity and ability to maintain shape. Of course, solids can still bend, crack, stretch, or deform under enough force, but their general behavior reflects an underlying structural order. Their stability comes from strong relationships among their particles. Liquids flow while maintaining a definite volume. Their particles stay close enough together that the liquid does not expand to fill all available space like a gas, but they can move around each other enough to allow flow. This gives liquids their special combination of freedom and cohesion. They can take the shape of a container while still keeping a fairly fixed amount of space occupied. Physics describes this not as a vague property of wetness, but as a result of particle behavior. Gases expand to fill their containers because their particles move more freely and occupy far more space on average. There is much less constraint keeping them close together, so they spread out until the available volume is filled. This is why a gas does not keep a fixed shape or volume on its own. It also explains why gases are so sensitive to temperature and pressure changes. Their freedom of motion makes them both simple to model and rich in behavior. Plasma is often called the fourth state of matter. In plasma, enough energy is present that electrons are freed from atoms, creating a mixture of charged particles. This makes plasma behave quite differently from ordinary gases. Because of its charged nature, it can respond strongly to electric and magnetic fields. Plasma is common in the universe, even if it feels less common in daily life, making it a major state of matter in cosmic terms. In a plasma, electrons are freed from atoms, creating a gas of charged particles. This ionization changes how the material behaves at a very fundamental level. Instead of neutral atoms dominating the picture, there are now positive ions and free electrons interacting in collective ways. These interactions can produce complex and beautiful behavior. Plasma physics becomes especially important wherever temperatures are high and fields are strong. Because plasma is charged, magnetic and electric fields can strongly affect it. This means plasma can be guided, confined, accelerated, or shaped in ways that ordinary neutral gases cannot. That is one reason plasma appears in such important settings, from stars and lightning to fusion experiments. Charged matter does not simply drift, it responds to fields in dynamic ways. Plasma is where particle motion and field structure become deeply intertwined. Stars are made largely of plasma. The high temperatures inside stars prevent electrons and nuclei from staying bound together as ordinary neutral atoms in the familiar way. This means the Sun and other stars are not glowing balls of ordinary gas in the everyday sense, but enormous plasma systems. Their light, heat, magnetic behavior, and internal dynamics all depend on that fact. A major part of the visible universe shines in the plasma state. Fusion research on Earth also requires making and controlling plasma. To bring light nuclei close enough together to fuse, extremely high temperatures are usually needed, and at those temperatures matter becomes plasma. The challenge is not only creating such a state, but holding it stable and useful long enough for net energy gain. This makes fusion both scientifically exciting and technically demanding. It is a field where plasma behavior becomes central. A tokamak confines plasma in a torus or donut shape, using magnetic fields. The reason for this design is that very hot plasma cannot simply be held in an ordinary solid container without damaging it and cooling too quickly. Magnetic fields offer a way to guide and contain the charged particles without direct contact in the usual sense. The torus shape helps support the necessary field geometry. It is a sophisticated response to a very difficult physical problem. One set of coils produces a toroidal magnetic field around the long way of the torus. This field is one of the essential ingredients in keeping the plasma organized inside the tokamak. Different field components work together to help guide particle motion and reduce losses. The geometry matters enormously because plasma can be unstable and difficult to confine. Fusion research depends on translating electromagnetic theory into precise magnetic architecture. Fusion researchers regard tokamaks as one of the leading concepts for future fusion power plants. This does not mean all challenges are solved, but it does show how promising the approach has become. Tokamaks have been studied for decades because they offer a physically plausible route to controlled fusion energy. They represent one of the most serious efforts to turn stellar-style processes into a human energy source. Physics here is not only theoretical, it is directly tied to possible future technology. Fusion reactions involving deuterium and tritium release large amounts of energy. These isotopes of hydrogen can fuse under the right conditions, and part of the mass difference between the starting and ending states appears as released energy. This is one of the clearest large-scale examples of the mass-energy relationship in action. Fusion is attractive because it offers the possibility of high energy yield from light nuclei. But reaching and controlling the necessary conditions remains difficult. In proposed fusion paths, neutrons from deuterium-tritium reactions would be a major route for extracting usable power. These neutrons carry a substantial fraction of the released energy and can transfer that energy to surrounding materials, which may then be used to produce heat and ultimately electricity. So the fusion reaction itself is only part of the system. The surrounding engineering must also capture and manage the energy efficiently. This is how basic nuclear physics connects to practical power design. Fluids can flow smoothly or turbulently depending on conditions such as speed, viscosity, and geometry. Smooth flow is more orderly, while turbulent flow contains swirling, chaotic motion across many scales. Both are real and important, but turbulence is often much harder to predict in detail. The difference affects water systems, aircraft, weather, blood flow, and industrial design. Fluid motion can look simple from far away, while hiding great complexity within it. Turbulence is one of the great practical challenges of physics because it produces complex motion across many scales. In turbulent flow, energy can move through large eddies, smaller swirls, and tiny dissipative motions all at once. This makes exact prediction extremely difficult, even when the basic laws are known. Turbulence is a reminder that having the equations does not always mean having an easy solution. Nature can remain complicated even under clear rules. Viscosity measures a fluid's resistance to flow. A highly viscous fluid flows more reluctantly, while a low-viscosity fluid moves more easily. Honey and water provide an easy everyday contrast. Viscosity affects energy loss, mixing, drag, and the transition between different flow behaviors. It is one of the key properties that tells us how a fluid will respond when forces are applied. Pressure gradients can drive fluid motion. If one region has higher pressure than another, the fluid tends to move in a way that reduces that difference. This is a major driver behind winds, pumping systems, and many natural and engineered flows. The idea is simple, but the resulting motion can become very complex depending on obstacles, viscosity, temperature, and other factors. Fluid motion often begins with an imbalance. Many weather patterns, ocean flows, and industrial systems are fluid physics problems. Air and water are both fluids, and so are many substances used in engineering. This means fluid physics is not a narrow specialty, but a major part of understanding the world. Storm systems, river motion, blood flow, fuel lines, and ventilation all depend on the same broad ideas. Once again, physics links ordinary experience to larger systems through shared principles. Crystals are solids with repeating atomic arrangements. Their particles are not placed randomly, but organized into ordered patterns that repeat through space. This repeating structure gives crystals many of their characteristic properties, including how they break, conduct, reflect light, or respond to stress. The beauty of a crystal on the outside reflects a deep order on the inside. Physics and geometry meet very clearly in crystalline matter. Some solids, such as glasses, lack long-range crystal order. They may still be solid in the sense that they hold shape, but their internal arrangement is not built on the same repeating pattern found in crystals. This difference affects their optical, mechanical, and thermal properties. It shows that solid is not a single microscopic arrangement, but a broader behavioral category. Structure matters even within the same overall phase. Material properties like strength, conductivity, and melting behavior depend strongly on atomic arrangement. Two materials made of similar ingredients can behave very differently if their internal structures differ. This is why materials science pays so much attention not only to composition, but also to pattern, defects, and bonding. Physics teaches that what matter is made of is only part of the story. How the matter is arranged is just as important. Quasi-crystals have ordered patterns without the simple periodic repetition seen in ordinary crystals. They are structured, but not in the familiar repeating way expected from standard crystal symmetry. This made them deeply interesting when they were identified because they challenged earlier expectations about what ordered solids could look like. Quasi-crystals show that nature sometimes chooses forms more subtle than our first categories suggest. Order does not always require simple repetition. Physics of materials often begins with the idea that microscopic structure controls macroscopic behavior. What we feel as hardness, flexibility, conductivity, brittleness, or transparency is usually rooted in how atoms are arranged and how they interact. A material's large-scale behavior is often the visible result of invisible structure. This is one of the central lessons of condensed matter and materials physics. The small shapes the large. Atoms consist of a tiny nucleus surrounded by electrons. The nucleus contains protons and neutrons, while the electrons occupy regions around it according to quantum rules. Although atoms are among the basic building blocks of ordinary matter, their internal structure is already rich and subtle. They are not solid little balls in the simple classical sense. Even a single atom contains layers of physical meaning. Most of an atom's volume is not packed with matter the way solid objects seem to be on everyday scales. The nucleus is extremely small compared with the total size of the atom, and the electrons occupy quantum states spread across the surrounding region. This means ordinary matter is structured in a way very different from how it looks to human senses. Solidity in daily life comes from forces and quantum rules, not from atoms being densely filled miniature pebbles. Physics often overturns visual intuition at small scales. Electrons in atoms occupy quantum states rather than little planetary orbits in the classical sense. The old image of electrons circling the nucleus like planets around the sun is useful only as a rough historical stepping stone. In quantum physics, electrons are described by allowed states with specific energies and probability structures. This gives atoms their stable patterns and distinct behavior. The microscopic world follows rules that are more subtle than simple little mechanical tracks. Atoms absorb and emit light in discrete amounts because their allowed energy states are quantized. This means an atom cannot usually take on just any energy it pleases. Instead, it occupies certain permitted levels, and when it moves between them, it absorbs or releases specific packets of energy. That is why the light associated with atoms appears in distinct spectral lines rather than as a completely smooth spread. Quantum physics turns atoms into systems with built-in steps rather than continuous ramps. Quantum theory explains why identical atoms produce repeatable spectral fingerprints. If two atoms of the same kind have the same internal structure, then the allowed energy differences inside them are also the same. That means they absorb and emit the same characteristic wavelengths under similar conditions. This repeatability is one reason spectroscopy is so powerful. The internal design of atoms becomes visible through the light they interact with. The Planck relation links a photon's energy to its frequency. In simple terms, the higher the frequency of the light, the greater the energy carried by each photon. This idea helped reveal that light is not only wave-like, but also comes in discrete energy packets. It was one of the key steps in the birth of quantum physics. A smooth-looking beam of light, when examined deeply, also has a particle-like energy structure. Higher frequency light carries more energy per photon than lower frequency light. That means one photon of very high frequency radiation can be far more energetic than one photon of radio or infrared light. This does not necessarily tell you how many photons there are, but it does tell you about the energy each one individually carries. Physics often separates these ideas carefully. Brightness and photon energy are related to light, but they are not the same thing. This is why gamma rays are more energetic than visible light, and visible light is more energetic than radio waves. All of these belong to the electromagnetic spectrum, but their photon energies differ because their frequencies differ. The same general kind of radiation can therefore interact with matter in very different ways depending on where it sits in the spectrum. This is why some radiation is useful for communication, some for vision, and some for medical imaging or high-energy astrophysics. The difference in frequency changes the entire style of interaction. Quantization first entered physics partly through attempts to explain how energy is exchanged by radiation. Classical ideas were struggling to describe certain thermal and radiative phenomena correctly, and the solution required a new assumption. Energy was not always exchanged continuously, but sometimes in discrete amounts. That small shift in thinking became one of the great turning points in science. Quantum theory did not begin as a desire to sound strange. It began as an effort to explain real measurements honestly. A tiny constant, the Planck constant, sets the scale at which quantum discreteness becomes important. It appears in many of the basic equations of quantum physics and helps mark the difference between quantum scale behavior and the smoother behavior that often emerges in larger systems. The constant is extremely small, which is part of why quantum effects are not always obvious in ordinary life. Yet at atomic and subatomic scales, it becomes fundamental. A very small number helps shape an enormous field of physics. Quantum physics does not say everything is random in every way. It gives precise probabilities and rules for how systems evolve. This is an important point because quantum theory is often described too loosely as pure uncertainty. In reality, it is highly structured and mathematically exact in how it assigns probabilities and predicts patterns. What is uncertain is often the specific outcome of a single measurement, not the overall framework. The theory is subtle, but not vague. Some quantities can only take certain values in bound quantum systems. An electron in an atom, for example, is not free to possess just any energy while remaining bound to that atom. Instead, it is limited to allowed states. This is one of the reasons atoms are stable and have recognizable spectral signatures. The world at small scales often behaves in steps instead of smooth continua. Measurement plays a special role in quantum theory because outcomes come in discrete possibilities with probabilities. Before measurement, quantum systems are described in ways that do not map neatly onto everyday expectations of definite hidden values for everything. When a measurement is made, a specific outcome is obtained, and a theory tells us the chances of the various possibilities. This is one reason quantum physics feels conceptually unusual. It asks us to think carefully about what it means to describe a system before and during observation. Wave-particle duality reflects that light and matter show both wave-like and particle-like behavior in different experiments. Light can interfere and diffract like a wave, yet it can also arrive in discrete photons. Matter, such as electrons, can also produce interference patterns while still being detected in localized events. This does not mean things are switching costumes in a theatrical way. It means the quantum world requires a description richer than the old simple categories of wave or particle alone. Quantum theory is one of the most tested frameworks in science, despite sounding counterintuitive at first. Many of its predictions have been checked again and again in experiments involving atoms, photons, solids, nuclei, and advanced technologies. The results have been stunningly successful. Much of modern electronics, lasers, spectroscopy, and precision measurement depends on quantum ideas being correct. So even though quantum theory may feel strange, it is not fragile speculation. It is deeply supported by evidence. The Pauli exclusion principle helps explain why matter has structure and why electrons stack into shells in atoms. He places a restriction on how certain particles, such as electrons, can occupy quantum states. Because electrons cannot all collapse into the same state in the same simple way, atoms develop layered arrangements of electrons. This helps create the richness of chemistry and the stability of matter. A subtle quantum rule ends up shaping the everyday world. Those electron arrangements shape the periodic table and chemical behavior. The way electrons fill available states determines how atoms bond, react, and combine. This is why elements with similar outer electron structures tend to share chemical properties. The periodic table is therefore not just a list of substances. It is a visible map of quantum structure. Chemistry, in a deep sense, grows out of quantum rules. Quantum tunneling allows particles to cross barriers that classical particles would not surmount the same way. In classical physics, a particle without enough energy to climb over a barrier should simply be blocked. In quantum mechanics, however, there can still be a real probability of appearing on the other side. This is not because the barrier vanishes, but because the quantum description allows behavior that has no exact classical equivalent. Tunneling is one of the clearest examples of how quantum physics changes what is physically possible. Tunneling is important in phenomena ranging from radioactive decay to some electronic devices. In radioactive decay, particles can tunnel out of nuclei even when classical reasoning would suggest they should remain trapped. In technology, tunneling can be used in specialized components and measurement tools. So this is not just a strange theoretical curiosity. It is both a natural process and a practical effect with real-world applications. Much of ordinary matter's stability depends on quantum rules that never show themselves directly at human scales. The solidity of objects, the shape of atoms, the behavior of electrons, and the structure of chemical matter all depend on quantum principles operating quietly underneath daily life. We do not usually see these rules directly, but we constantly live inside their consequences. This is one of the remarkable features of physics. The familiar world rests on unfamiliar foundations. Entanglement is a quantum correlation stronger than any classical picture based only on local hidden properties. When systems are entangled, their measurement outcomes are connected in ways that cannot be explained by pretending each one was carrying a complete private set of independent instructions all along. This does not mean information is being casually sent faster than light in ordinary use, but it does mean the structure of quantum correlations is deeper than classical intuition expected. Entanglement is one of the most powerful and famous features of quantum theory. Quantum information science uses superposition and entanglement as resources rather than oddities to be ignored. Instead of treating these effects as merely philosophical puzzles, researchers try to harness them for tasks such as computing, communication, and precision measurement. This is a major shift in attitude. What once seemed like the strangest parts of quantum physics are now being developed into useful tools. Physics often progresses by turning mystery into method. Some quantum computing platforms use superconducting circuits. In these systems, carefully designed electrical circuits behave quantum mechanically under the right low-temperature conditions. Researchers can manipulate and measure these quantum states to perform computational operations. This approach is one of several serious paths toward quantum computing. It shows that quantum behavior is not limited to isolated atoms alone, but can also be engineered into larger devices. Others use trapped ions, atoms, photons, or related quantum systems. Each platform has its own strengths, challenges, and ways of storing and controlling quantum information. Trapped ions can be extremely precise, photons are useful for communication, and neutral atoms and other systems offer different advantages in scaling or coherence. The field is still developing, so no single method has permanently won every category. This diversity reflects how rich quantum engineering has become. Precision measurement and quantum computing often overlap because both require extraordinary control of quantum states. If you want to build a useful quantum computer, you must prepare, protect, manipulate, and read out quantum systems with great accuracy. The same is true when you want to make a clock or sensor of extreme precision. This overlap means advances in one area can often support the other. Quantum technology is connected not just by theory, but by shared experimental demands. Radioactivity comes from unstable atomic nuclei, changing into more stable forms. Some nuclei are not in their lowest or most stable arrangement, and over time they can transform by emitting particles or radiation. This process is natural and does not require human intervention to occur. Different unstable nuclei decay in different ways and on different timescales. Radioactivity is therefore not a single event, but a whole family of nuclear changes. Nuclear physics studies the structure, forces, and transformations of nuclei. It asks how protons and neutrons are arranged, why some nuclei are stable while others are not, and what happens when nuclei split, combine, or emit radiation. This field connects deeply with energy production, medicine, astrophysics, and fundamental science. Nuclei are small, but their behavior has enormous consequences. Nuclear physics sits at the intersection of the tiny and the powerful. Nuclear energy is tied to binding energy, which affects how strongly nucleons are held together. Protons and neutrons inside a nucleus are bound by powerful interactions, and the exact arrangement affects how much energy is associated with the system. Differences in binding energy help explain why some nuclear transformations release energy. This is not because energy appears from nowhere, but because the final arrangement can be more tightly bound than the initial one. The balance changes, and energy is released. Fission splits heavy nuclei, while fusion combines light nuclei. These are two different nuclear pathways, but both can produce energy under the right conditions. Fission works by breaking apart very heavy nuclei into smaller ones, while fusion works by joining light nuclei into heavier ones. Each process depends on the structure of binding energy across different nuclei. Though opposite in direction, both show how nuclear structure can be turned into released energy. Both can release energy because the total mass-energy balance changes between initial and final states. The products of a nuclear reaction may have a slightly lower total mass than the starting materials, and that difference corresponds to released energy through the mass-energy relationship. This is one of the clearest examples of mass and energy being directly linked. Nuclear reactions make that connection visible on a practical scale. Matter itself carries hidden energetic structure. The Standard Model is the current leading theory describing known elementary particles and the electromagnetic, weak, and strong interactions. It provides a framework for understanding many of the smallest known building blocks of matter and the main non-gravitational forces acting among them. It is one of the most successful theories in all of science, with many predictions confirmed experimentally. At the same time, it is not believed to be the final theory of everything. It is powerful but not complete. Gravity is not included in the Standard Model, which is one reason physicists know the model is incomplete as a final theory. The Standard Model handles several fundamental interactions beautifully, but it does not provide a full quantum account of gravity in the same way. This leaves an important gap, especially for situations where both gravity and quantum effects matter strongly. So even a very successful theory can still be unfinished. Physics moves forward by recognizing both strengths and limits. The Standard Model includes matter particles and force-carrying particles. Some particles make up the substance of matter, while others mediate interactions among them. This organization gives the theory a clear internal structure. It is not just a list of particles, but a system describing how they fit together. That balance between ingredients and interactions is one reason the model is so elegant. Quarks combine to form particles such as protons and neutrons. Quarks do not usually appear alone in ordinary conditions, but instead join into composite particles. Protons and neutrons, which make up atomic nuclei, are therefore not elementary in the deepest sense. They have internal structure. This was a major advance in understanding matter at smaller scales. Leptons include the electron and neutrinos. Unlike protons and neutrons, these are treated in the Standard Model as elementary particles, not known to be built from smaller parts in the same way. Electrons are central to atoms, electricity, and chemistry, while neutrinos are famously elusive and interact only weakly with matter. Both belong to the same broad family, even though they behave very differently. Particle physics groups them by deeper properties rather than everyday familiarity. The Higgs boson is the only known fundamental particle with zero spin in the Standard Model. This makes it special among the known fundamental particles. Spin in particle physics is a quantum property, and most other fundamental particles fall into different spin categories. The Higgs stands out not only because of its role, but also because of this distinctive feature. It occupies a very unusual place in the model's particle family. It has no electric charge and does not interact through the strong force. That helps determine how it is produced, how it behaves, and how it can be detected indirectly through its decay products. In particle physics, these properties are not minor labels. They shape the particle's whole experimental life. A particle's charge and interactions tell scientists where to look and what kinds of traces to expect. The Higgs boson is not found lying around in nature, the way rocks are. It has to be created in high-energy collisions. Because it is heavy and unstable, it does not remain present as a long-lived everyday particle. Instead, it is produced briefly in energetic conditions such as those created in powerful particle accelerators. This means the Higgs is known not by picking one up, but by creating it and analyzing what follows. Modern particle physics often works this way. Once created, it decays quickly into other particles that detectors can register. Scientists therefore do not usually observe a Higgs boson directly in a simple visual sense. Instead, they reconstruct its presence from the patterns left by the particles it turns into. This is a common strategy in high-energy physics, where many important particles exist only briefly. The event is inferred from traces, not seen like an everyday object. Its discovery in 2012 was a landmark confirmation of the Standard Model's Higgs mechanism. This was a major moment in modern physics because it confounded a crucial missing piece of a very successful theory. The discovery did not mean every question was solved, but it strongly validated a central part of the model. It showed that decades of theoretical work and experimental effort had converged successfully. Some discoveries complete a chapter even while opening new ones. The top quark is the heaviest known elementary particle. Its large mass makes it especially interesting because mass is deeply connected to the Higgs field in the Standard Model. The top quark therefore occupies a privileged place in many precision tests and theoretical discussions. It is a reminder that not all elementary particles are similar in scale or importance. Some stand out because of how extreme their properties are. Because of that, it couples especially strongly to the Higgs field. In simple terms, the top quark has one of the strongest relationships to the Higgs sector among known particles. This makes it especially valuable for studying whether the Higgs behaves exactly as expected. If subtle deviations from the standard model exist, top Higgs interactions are one place scientists may notice them. The heaviest known elementary particle becomes a probe of one of the deepest modern theories. Studying top Higgs interactions is one way physicists test whether the Higgs sector behaves exactly as expected. Precise measurements can reveal whether the standard model description remains fully accurate, or whether small deviations point toward new physics. This is how frontier physics often works. Scientists do not only search for entirely new particles, they also inspect known particles with great care, looking for tiny cracks in the current picture. Particle physics often learns about short-lived particles by analyzing the products they leave behind. Many fundamental particles exist for such brief moments that they are gone almost immediately after being created. What remains are the decay products, tracks, energies, and interaction signatures. By studying those traces, physicists can reconstruct what happened. This is a science of careful inference as much as direct detection. Detectors are designed less like cameras for tiny objects and more like systems for reconstructing invisible events from traces. They measure paths, energies, times, deposited signals, and many other features. From those pieces, scientists build a picture of the underlying collision or decay. This is why particle physics experiments are both technological and interpretive. They convert fleeting microscopic events into readable patterns. Antimatter contains particles with the same mass as their matter counterparts, but opposite charges or related quantum numbers. An antielectron, for example, has the same mass as an electron, but opposite electric charge. Antimatter is not fantasy matter from a different universe. It is part of the known framework of particle physics. The existence of such mirrored partners is one of the elegant symmetries built into modern theory. When matter and antimatter meet, they can annihilate and convert their mass into other forms of energy and particles. This process is a dramatic illustration of Massenergy conversion. The original matter and antimatter do not simply disappear without consequence. Their mass contributes to the energy and products that emerge. Annihilation is therefore both destructive and revealing, showing how deeply matter is tied to energy. Physicists continue to investigate why the observable universe is dominated by matter rather than antimatter. If the early universe had produced matter and antimatter in exactly equal lasting amounts with no imbalance, much of it might have annihilated away far more completely. Yet a matter-dominated cosmos clearly remains. This means some asymmetry must have mattered. Understanding that asymmetry is one of the major open problems in fundamental physics. Symmetry breaking is a recurring theme in high-energy physics because tiny asymmetries can have huge cosmic consequences. A universe that begins in a nearly balanced way can evolve into one with specific structures and preferences if certain symmetries are not preserved exactly. This idea appears in several areas of modern theory. It is one of the reasons physicists care so much about very small differences. Small imbalances can shape the entire large-scale outcome. Particle accelerators let scientists recreate conditions energetic enough to probe these questions experimentally. By colliding particles at high speed, researchers can produce rare events, heavy particles, and interaction patterns not normally accessible in everyday conditions. Accelerators do not recreate the whole universe, of course, but they do create controlled glimpses into the physics of very high energy. They are among the most powerful tools humans have built for exploring the small. In them, theory and experiment meet at the frontier. Relativity begins from the idea that the laws of physics are the same in all suitable frames. This means that no smooth, non-accelerating frame of reference is secretly the one preferred by nature. Observers moving steadily relative to one another should still find that the same basic laws hold. That simple principle has enormous consequences. It pushes physics away from old assumptions about absolute motion and toward a deeper structure of space-time. Special relativity also takes the speed of light in vacuum as the same for all inertial observers. This is a startling idea because everyday intuition suggests that speed should simply add and subtract in the usual way for everyone. But when light is involved, space-time itself adjusts, so that this speed remains constant. From that come effects that feel strange at first but are now well established. A single constant reshapes our understanding of motion. From those principles come effects such as time dilation and length contraction. Time dilation means that moving clocks can be measured to tick differently relative to one another, and length contraction means that distances along the direction of motion can be measured differently as well. These are not errors or illusions in the simple sense. They are consequences of the structure of space-time itself. Relativity teaches that time and distance are not fixed background containers, but part of the physical fabric of the world. Earthquakes generate seismic waves that travel through the planet. When rock suddenly slips and releases stored stress, that energy spreads outward in wave form through Earth's layers. These waves can move through deep interior regions and along the surface, carrying information about both the earthquake and the structure of the planet itself. In that sense, an earthquake is not only a destructive event at the surface. It is also a physical signal moving through Earth like a message written in motion. Different seismic waves affect structures differently depending on building size and the wave period. A building is not shaken in exactly the same way by every kind of ground motion. Its height, flexibility, and design influence how it responds to the wave passing through the ground below it. This means that the same earthquake can have very different effects on different structures in the same city. Physics helps explain why damage patterns are often selective rather than uniform. Long-period waves can shake skyscrapers more strongly than short-period waves. Tall buildings often respond more to slower, more drawn-out oscillations because those motions line up better with the natural way such structures sway. Shorter buildings may respond differently because their own preferred motion timescales are not the same. This is one reason engineers care deeply about vibration behavior, not just raw force. How long each wave cycle lasts can matter just as much as how strong the shaking is. Resonance occurs when a system is driven near one of its natural frequencies. At that point, even a repeated push that is not individually huge can build into large motion if the timing matches the system's preferred rhythm. This is why a child on a swing can go higher from small pushes given at the right time. It is also why buildings, bridges, machines, and musical instruments can behave so strongly under the right conditions. Physics often shows that timing can amplify effects without increasing the force itself. In physics, matching timescales can matter as much as raw force. A system may barely notice a badly timed push, but respond strongly to a well-timed one. This is true in vibrations, waves, motion, and many other areas. It reminds us that physical behavior is shaped not only by how much energy is involved, but also by how that energy is delivered. Sometimes the rhythm of an interaction is the main story. Thunder is a consequence of lightning rapidly heating air, causing a sudden expansion that launches a sound wave. The lightning channel becomes extremely hot in a very short time, and the nearby air responds by expanding violently. That rapid expansion creates a pressure disturbance, and that disturbance travels outward as sound. Thunder is therefore the audible result of the atmosphere reacting to an electrical discharge. A flash in the sky becomes a wave in the air. Lightning itself is an electrical discharge. It occurs when electric charge builds up enough in the atmosphere for current to surge through a path in the air. Air normally resists current strongly, but under the right conditions, the electrical potential becomes so great that breakdown happens. The result is a bright, fast, energetic discharge. What looks sudden and chaotic is still governed by the rules of charge, field, and current. Aurorae are tied to geomagnetic storm activity and processes in Earth's magnetosphere. When energetic particles and changing magnetic conditions interact with near-Earth space, the upper atmosphere can begin to glow. This glow is not simply a decorative effect in the night sky. It is part of a larger chain of electromagnetic interactions involving the Sun, Earth's magnetic field, and atmospheric particles. The colors and shifting curtains of aurora are visible signs of space physics becoming visible to human eyes. Geomagnetic storms happen when energy from the solar wind is transferred efficiently into near-Earth space. The solar wind carries plasma and magnetic fields outward from the Sun, and under certain conditions, this energy interacts strongly with Earth's magnetic environment. When the coupling is effective, the magnetosphere can become highly disturbed. These disturbances can drive aurorae and influence technological systems. A storm in space is not made of rain and wind, but of charged particles and magnetic structure. The sky can glow, crack, or ripple because of electromagnetic physics acting on a planetary scale. Lightning, aurorae, and related phenomena are reminders that the atmosphere and near-Earth space are not quiet, empty surroundings. They are active physical systems shaped by fields, charges, currents, and radiation. Some of these effects are brief and local, while others involve global magnetic behavior. The sky is often more dynamic than it first appears. Earth's magnetosphere responds dynamically to changing solar wind conditions. It is not a rigid shell that passively blocks everything. Instead, it stretches, compresses, stores energy, and releases it as conditions from the Sun change. This makes it a living system in the physical sense, always reacting to its environment. The magnetic surroundings of Earth are full of motion and structure, even though they are invisible to ordinary sight. Magnetic measurements from satellites help forecasters identify the buildup and release of energy during geomagnetic storms. By observing how fields and charged particles behave in space, scientists can detect patterns that signal growing disturbance or changing conditions. These measurements matter because the effects of space weather can reach into systems people depend on every day. The monitoring of invisible fields becomes a practical service. Quiet data from orbit can reveal active processes around the planet. Space weather can affect radio communication, GPS, satellites, and electric power systems. This is one of the reasons the topic matters so much beyond science itself. Disturbances in near-Earth space can interfere with signals, change satellite conditions, and even contribute to problems in electrical infrastructure. So space weather is not only about beautiful auroras or solar activity headlines. It is also about how electromagnetic conditions in space reach into daily technological life. The aurora is not just visually striking, it is also a sign that energy is moving through geospace. When people look at an aurora, they are seeing part of a larger energy transfer process, involving charged particles, magnetic fields, and Earth's upper atmosphere. The beauty of it is real, but so is the physics behind it. A glowing sky can be a sign that planetary electromagnetic systems are actively responding to solar influence. Light in the night can be evidence of motion in space. Physics of space weather matters because invisible fields can influence everyday technological systems on Earth. Many people rarely think about magnetic conditions in near-Earth space, yet those conditions can affect navigation, communication, and infrastructure. This is a good example of how modern life depends on physical environments far beyond immediate human perception. What cannot be seen directly can still shape practical outcomes. Invisible structure often matters greatly. Mass and energy are related by the famous equation E equals mc2. This equation says that mass can be understood as a form of energy, with the factor of the speed of light squared showing just how large that connection is. It does not mean ordinary objects constantly explode into light, but it does mean matter contains immense energy in principle. Nuclear processes reveal this relationship especially clearly. It is one of the most widely recognized equations because it expresses a deep truth in a compact form. Relativity changed not only physics formulas, but the basic concepts of space and time. Before relativity, many people pictured time as a universal flow and space as a neutral stage where events simply occurred. Relativity replaced that picture with something more intertwined and subtle. Measurements of time and distance depend on motion and gravity in lawful ways. This was not just a technical correction, but a transformation in how reality itself was described. General relativity describes gravity not as a conventional force field alone, but as the curvature of space-time produced by mass energy. In this framework, matter and energy influence the geometry of space-time, and objects move along paths shaped by that geometry. This means gravity is not merely a pull acting across distance in the old intuitive sense. It is also a property of the structure of space-time itself. The result is one of the most elegant ideas in all of physics. In that picture, freely falling objects follow paths shaped by space-time geometry. A falling object is not simply being yanked downward by an invisible rope-like force. Instead, it follows the natural route allowed by curved space-time. This is one reason orbiting bodies can be understood so beautifully in relativity. Motion under gravity becomes geometry in action. General relativity has successfully described gravitational phenomena observed so far on many scales. It has been used to explain planetary motion, the bending of light, time effects near gravity, black holes, gravitational waves, and much more. Its success is one reason it remains central to modern physics. Few theories have described such a wide range of phenomena so accurately. It is one of the great intellectual achievements of science. It still does not incorporate the quantum nature of matter and non-gravitational forces in a complete unified way. This is one of the important limits of our current understanding. Quantum physics describes the small world with great success, and general relativity describes gravity with great success, yet the two are not fully merged into one complete framework. That means the deepest description of reality is still unfinished. Physics remains a living field because the foundations are still being explored. That gap is one of the major reasons physicists search for deeper theories of gravity. Scientists want a framework that can describe gravity consistently alongside quantum principles, especially in extreme settings where both should matter strongly. Places like black hole interiors or the earliest moments of the universe may require such a theory. The search continues not because current physics has failed, but because its two great pillars do not yet fully join. Superconductors can carry electric current with essentially no electrical resistance under the right conditions. That means current can flow through them without the ordinary kind of resistive energy loss seen in common conductors. This is a remarkable state of matter because resistance is so familiar in everyday electrical systems. Superconductivity shows that under the right circumstances, electrons can behave collectively in an unusually ordered way. A material can enter a state that feels almost impossible by ordinary standards. Superconductivity was discovered in 1911. This discovery opened a completely new chapter in the study of matter because it revealed that cooling certain materials enough could produce behavior unlike ordinary conduction. It was one of those moments when nature showed a possibility that theory had not yet fully explained. Discoveries like this are part of what keeps physics alive. Matter can still surprise us. A major theoretical explanation arrived in 1957, but the subject remains active because many superconductors do not fit the simplest picture perfectly. The theory explained a great deal and became one of the triumphs of modern condensed matter physics. Yet superconductivity did not become a finished subject after that. New materials and unusual forms kept the field lively. Physics often works this way. One major explanation solves much, but also reveals new layers of complexity. Superconducting technologies are important for strong magnets used in MRI, accelerators, and some experimental fusion systems. Because superconductors can support large currents with extremely low losses, they are valuable wherever strong, stable magnetic fields are needed. This makes them practical as well as fascinating. A once surprising low temperature effect became a key tool in medicine and big science engineering. It is a fine example of basic physics turning into useful technology. A material can become technologically revolutionary when cooling changes how electrons move collectively. In ordinary conditions, electrons in a material may scatter in ways that produce resistance. In a superconducting state, their collective behavior changes dramatically, and the whole electrical character of the material transforms. That shift is not just a small improvement. It can open entirely new possibilities. Physics often finds that the most important changes happen when many particles begin acting together in new ways. High magnetic fields are important in both research and technology, from spectroscopy to fusion experiments. Strong fields can reveal subtle properties of matter, guide charged particles, shape plasmas, and support advanced imaging or measurement methods. They are not only dramatic laboratory features, but working tools across many fields. The ability to generate and control strong magnetic fields expanded what scientists and engineers could do. Field strength became a gateway to new precision and capability. Superconducting transmission lines are being explored because they could move power with far lower losses than ordinary lines. In principle, this could make electrical transport more efficient in certain settings, though practical challenges remain. The idea is appealing because so much energy in ordinary systems is lost as heat. A different material state offers the possibility of far gentler transport. It is one more way condensed matter physics might reshape infrastructure. Quasi-crystals and high-entropy alloys have become interesting platforms for studying unusual superconducting behavior. These materials bring together structure, disorder, composition, and collective electron behavior in ways that can produce surprising results. Scientists are interested in them because new kinds of arrangement may lead to new kinds of superconducting response. This reflects a broader theme in materials physics. When structure changes, possibilities change with it. Material physics often advances by finding new structures where known laws produce unexpected combinations of properties. The laws of physics may be familiar, yet new arrangements of atoms can still generate new behavior. This is part of why materials science remains so active. Discovery does not always require a new force of nature. Sometimes it comes from giving known forces a new stage on which to act. The frontier in condensed matter physics is often about collective behavior rather than new fundamental particles. When many particles interact together, they can form states and patterns that no single particle shows alone. These emergent behaviors are a major part of modern research. Superconductivity, magnetism, and many unusual materials belong to this realm. Physics at the frontier is not always about going smaller. Sometimes it is about understanding what many small things do together. Physics regularly turns abstract principles into tools, such as clocks, lasers, medical imaging, radio communication, and navigation systems. This is one of the quiet triumphs of the field. Ideas that begin as deep questions about nature often become reliable parts of everyday life. A theory about waves or atoms can eventually shape healthcare, travel, communication, and measurement. The path from concept to tool is one of the gentlest forms of scientific transformation. Precision timing is essential for modern navigation because accurate position finding depends on accurate time measurement. In systems such as satellite navigation, the travel time of signals must be known with great precision. Tiny timing errors can turn into significant position errors. This means that timekeeping is not just for clocks on walls or schedules on paper. In modern technology, time itself becomes part of location. Pendulum clocks were once the best land timekeepers, but they did not solve the problem of reliable timekeeping at sea. A pendulum works well when conditions are stable, but on a moving ship, the motion and environment make accurate operation much harder. This historical problem mattered greatly because navigation depended on knowing time well. The challenge of keeping good time pushed science, engineering, and exploration forward together. A clock problem became a world problem. Better clocks changed not only science but transportation, mapping, and global coordination. As timekeeping improved, so did navigation, communication, measurement, and the ability to synchronize activities across distance. This made clocks far more than household devices. They became infrastructure for modern society. Physics of timekeeping helped shape the connected world. Sometimes a basic physics problem becomes historically important because society starts depending on the answer. Good timekeeping is one example, but there are many others. Once transportation, communication, and precision technology rely on something, a subtle scientific issue becomes a practical necessity. This is one reason physics so often matters beyond the laboratory. The world begins to lean on its answers. Measurements matter so much in physics that the sea system ties its base units to fixed constants of nature, rather than physical artifacts. This approach is powerful because artifacts can change, wear down, or depend on location, while fundamental constants offer a more universal basis. By building units around constants, measurement becomes more stable and conceptually deeper. The units themselves become connected to the structure of nature. Precision begins at the level of definition. In the modern sea, the meter is defined through the exact speed of light in vacuum, and the second is tied to the cesium-133 atoms hyperfine transition. This means length and time are anchored to physical realities that can be reproduced and measured with extraordinary precision. Instead of relying on a bar stored somewhere or a less stable reference, the system uses nature itself. Measurement becomes a dialogue with constants and atomic behavior. Even basic units now carry a quiet touch of modern physics. The speed of light in vacuum is fixed exactly at 299, 792, 458 meters per second in the sea system. This exact value does not merely describe a measured speed. It also plays a role in defining the meter itself. That means the speed of light is not only important in relativity and optics, but also in the very structure of modern measurement. A universal constant becomes part of the ruler. The Planck constant is fixed exactly in the sea, linking measurements of mass, energy, and quantum behavior. Because the Planck constant sits at the heart of quantum physics, using it in the sea helps tie the measurement system to one of nature's most fundamental scales. This reflects a beautiful shift in metrology. Units are no longer based mainly on human-made reference objects. They are grounded in the deep architecture of the physical world. The elementary charge is also exact in the sea, which means electric current is now defined through a fundamental property of nature. Charge is one of the core ideas in electromagnetism, and anchoring units to it makes the system more universal and conceptually clean. What used to be treated more indirectly can now be tied to a basic constant. This is part of the modern effort to make measurement reflect nature as directly as possible. The Boltzmann constant gives a bridge between temperature and energy on the particle scale. It connects the large-scale idea of temperature with the microscopic energetic behavior of particles. This is one of the reasons thermodynamics and statistical physics fit together so deeply. Temperature is not just an everyday sensation of hot and cold. It also has a precise microscopic meaning, and the Boltzmann constant helps express that relationship. The Kelvin is now defined through the exact value of the Boltzmann constant, rather than through a special material sample. This means temperature, like other C quantities, is anchored more directly to a fundamental constant. It is a quiet but important improvement in the logic of measurement. Nature provides the basis rather than a special physical object. The way humans define temperature became more universal and more deeply physical. A physical constant is called fundamental because it appears again and again in basic theories, not because it must come with a visible object attached to it. Fundamental constants matter because they sit at the core of the equations that describe nature. They help shape the scale, structure, and relationships in physical law. Some of them are familiar by name, while others are known mostly within science. What makes them fundamental is their repeated role in the foundations. Frequency and time are deeply linked, which is why better clocks are also better frequency standards. A clock is, in a deep sense, a system that counts regular repetition. If the repetition is stable and well-known, then time can be measured with greater accuracy. This is why frequency lies at the heart of precision timekeeping. The calm regularity of oscillation becomes the basis of the flow of measured time. Atomic clocks work by using atoms as highly stable natural oscillators. Atoms provide transitions with extremely regular frequencies, making them far more reliable than many older mechanical or macroscopic systems. This is why atomic clocks became the gold standard for high-precision timekeeping. They do not rely on gears or swinging pendulums in the traditional way. Instead, they listen to the steady behavior of atoms. The first practical atomic clocks used beams of cesium atoms traveling through a long tube. These systems were an early realization that atomic regularity could anchor time more precisely than earlier technologies. The atoms moved through carefully designed equipment that allowed scientists to measure and lock onto a very specific transition frequency. This was a turning point in timekeeping. A new era began when the clock's heart became atomic rather than mechanical. Beam clocks have been a reliable basis for precise timekeeping since the 1950s. For decades, they provided the backbone of highly accurate standards and helped transform measurement, navigation, and scientific precision. Their success showed that atomic methods were not just interesting laboratory ideas. They were practical and dependable. Timekeeping became one of the clearest examples of quantum and atomic physics entering the everyday structure of civilization. Optical atomic clocks are even more precise than older microwave atomic clocks because they use much higher frequencies. A higher frequency provides more oscillations to count, which can allow finer timing resolution when everything else is controlled well. This makes optical clocks some of the most precise devices humans have ever built. They are not merely better clocks in a small step-by-step sense. They are part of an ongoing refinement in how accurately time itself can be defined. A major trick behind optical lattice clocks is the magic wavelength, where trapping light can hold atoms without ruining the clock signal. Normally, trapping atoms with light could disturb the very transition you want to measure. The magic wavelength is a carefully chosen condition that allows the atoms to be held while minimizing that problem. It is a beautiful example of precision physics. Light is used both as a tool and as something that must be delicately controlled. Precision clock comparisons are so sensitive that they can test whether certain fundamental constants change over time. This means clocks are not only tools for keeping time. They can also become experiments about the deepest stability of physical law. When clocks reach extreme precision, comparing them may reveal whether nature's constants remain exactly the same across time and conditions. Measurement becomes a way of asking philosophical questions in experimental form. Physics often advances not only by discovering new particles or forces, but by learning to measure old things much more accurately. Sometimes no brand new object is found, yet understanding still deepens, because precision improves. Better measurement can confirm theories, expose tiny deviations, or open entirely new areas of inquiry. Progress is often quiet before it is dramatic. A sharper instrument can change the map of knowledge. Some of the most exact numbers in science come from metrology, the physics of measurement itself. This may sound gentle and technical, but it is one of the most foundational parts of the whole subject. Before theories can be tested and technologies can be trusted, quantities must be defined and measured with extraordinary care. In that quiet discipline, science refines its own language. And in that stillness of precision, the world becomes just a little clearer and a little more calm.